So in this and the next segment, we'll walk through the actual risk management process at a high level. As I mentioned before, as we walk through medical software lifecycle in weeks 5 through 10 of this class, we'll revisit this topic in the specific context of each of the steps of the process. So this is a flow chart that we will use to serve as a roadmap, and we'll follow these 4 steps: risk analysis, risk evaluation, risk control, and evaluation of residual risk. And this would be the roadmap we will follow. So the first step is risk analysis. And the risk analysis fundamentally consists of identifying the hazards. What could possibly go wrong? In the beginning, we make educated guesses. We have the prior history. This type of thing tends to fail. But as the process progresses, we learn from issues as they arise. We get tester and customer reports. We get reports from our programmers and say, well, this piece of code was really hard to write. This is something that should give us pause. And also we have the previous checklist from the guidance documents. We have to look at user risk and application risk and security risk. All of those things come into hazard identification. And so how does one estimate the risk? Risk is the combination of the probability and the severity of something going wrong. And in the hardware, we can get a sense of the probability through testing, right? We take a piece of equipment, say a surgical stapler, we test it 1,000 times, it fails 10 times. Now we have a ratio of a likelihood sense, okay? It's 1%. But software is really deterministic. So when random software failure is really a bug which only manifests itself when a certain set of inputs is given to the software. So really, it's not the probability of failure, it's the probability of conditions occurring. And this is a very important point. So software will always do the same thing given the same inputs. Most of the time. There are slight situations like random initializations, but for the most part, given a certain set of inputs, we're always going to get a certain set of outputs. So when we get a random software failure, it's not really a random software failure. It means that the inputs we gave to the software will always have led it to fail. It's just that we've never encountered this thing before. And because it is hard to test all possible conditions, some of these things stay there, some latent bugs stay there, which may manifest themselves when those conditions occur. And so it's important for us to code software such that it has a minimal feature set just to minimize all the conditions that could possibly happen. The other aspect here, as we continue, of course, is that hardware fails randomly because of sort of microstructural or manufacturing failures. Software doesn't have those kinds of issues. So let's look at an example of computing risk. We're going to talk about software, the probability of risk here. We're going to talk about software to measure tumor size from MRI. So we have images, we want to figure out how big a tumor is. The size is a critical input to the diagnosis of care. If you have a large tumor, we may have to go for immediate surgery radiation therapy. If the tumor is small, then we just monitor it and issues of that nature. So what's a hazard? A hazard here is that our software produces a bad measurement. Okay? We underestimate the size of the tumor. The sequence of events in which this could be problematic is that we have a measurement error and the radiologists fail to spot this. A hazard to situations now is if this error can lead to a bad diagnosis, and the harm to the patient could be that this failure of diagnosis can lead to a worse clinical outcome. So all of these things have probabilities associated with them, and the probability of this harm is a combination of all of those things. So let's sort of walk through them in a little bit more detail. Again, here's my chart here. Let's compute the probability of a hazardous situation first. So we define probabilities, and we're going to have a lot more to talk about this in week 9 of this class as numbers as between 0 and 1. 0, the event will never happen. 1, the event is certain. And let's say P subscript B is the measurement error, the probability of our software giving the wrong number. And P underscore D is the failure of the human in the loop to detect the error. Now, if those things are independent, the probability of a hazardous situation is the product. So if this thing is 0.2 and this thing is 0.1, now suddenly we have at 0.02 or 2% of having this kind of situation happen. So what is the probability of harm now? The probability of harm is we have to also account for the fact that not all hazard situations will lead to harm. Sometimes our error has no effect. We underestimated the tumor size by 20%, but the treatment would have been the same no matter what, so it doesn't really matter. Sometimes our underestimation leads to the wrong diagnosis, the wrong treatment, and that can have an effect. So we define that as a probability PB, and then the overall probability of harm is the product PHS PB. Now, realize all these numbers are less than 1, so what you want, and this is a standard risk mitigation exercise, so have a lot of these things multiplying each other because that reduces the risk. So this is almost, if you wish, a mathematical proof of the system of checks and balances. Now, computing such probabilities is far from trivial, and people can get into trouble by trying to be too accurate here. So we'll talk about qualitative probabilities in a minute. The other component of estimating risk is the severity of the harm. This is application specific and is often easier, and we often know what the consequences of the harm to the patient could be. If we underestimate tumor size and instead of prescribing treatment, we do nothing, what is the probability that the patient would suffer a severe adverse effect? We usually know that. So while you can use quantitative probabilities and things like 1% and 2% and 5%, sometimes it's just easier to use qualitative scales. And this is from a book by Vogel. We'll show a picture of the textbook actually in the next segment. And so sometimes we assign risk on a qualitative scale. So we have risk levels going 1 to 5. And so if the probability of harm is high and the severity of harm is high, we assign the risk to be 5. And as these things go down, if it's low and low, we're at 1, etc. And you can get the in-between. And let me define what I mean by low, medium, and high probabilities. Low means it's unlikely, perhaps. Medium is somewhat likely, and high is very likely. Now, when we start a project, one of the things we have to decide on early is what is the acceptable risk in this project. So it may be, depending on the application, that we could say, well, risk levels below 2 are okay, and risk levels above 2, we'll call them bad here. And so we work through, we assess the risk involved in every possible harm. If it's less than 2, if it's 2 or 1, we say, that's okay, we'll document. It means we talked about this, we're done. And if it's more than 2, now we work out through techniques to reduce the risk, and we're going to talk about risk control techniques in the next segment. So let's think a little bit about what increases the probability of software failure. Let's get a little bit of software specific here, and this is from a checklist from this book by Vogel, Medical Device Software Verification by then Compliance. It's a good book for professional engineers and it's highly recommended. The first thing that makes software fail is if it's large, so the size of the software item, and the second is the complexity of the software item. Those two combined can lead you to bad outcomes. So early in the pandemic, this tweet from Niall Ferguson, who's one of the expert epidemiologists in London, at Imperial College London, and he had written some code to model pandemics, and people were asking to see the code, and he said, look, we're cleaning up the code, so let you see it. And here's what he says: I'm conscious that lots of people would like to see and run the pandemic simulation code we're using to model control measures for COVID-19. To explain the background, this is a delay here. I wrote the code, thousands of lines of undocumented C 13 years ago to model flu pandemic. Now, any professional software engineer, anybody who has any experience in software, looks at this comment of 1,000 lines of undocumented C and says, this thing is unlikely to work perfectly, or it's likely to have significant bugs, because this is a large, complex piece of software. On top of this is undocumented. So the risk of failure in a piece of code like this is high. And one can ask questions of whether code like that should be used to make significant decisions, but that's another story. The other things that lead software to fail and increases the risk: inexperience of the developer or low skill, test inexperience or low skill if a tester fails to catch errors, changes made late or in stressful circumstances. The things you do late at night before a deadline are high risk. If the functionality is not well understood, documented, if the design isn't clear about what should be done, the code is unlikely to be clear either. And finally, a piece of software that has a history of problems. So in many software situations, one of those is if we have multi-processing, multi-threading piece of code that runs on multiple processors. That is often a source of problems. An experienced software engineer would look at that and say, let's check this piece of code more carefully. This is the kind of thing that makes software fail. So this concludes the first part of our discussion of the risk management process. In the second part, we'll continue with this flowchart and talk about risk control and other aspects of this process. Thank you.